Okay, welcome viewers for today's tutorials. My name is Moriza. So, last time we did a tutorial on alkenes. Today we shall do on alkenes. So, very first I shall introduce what alkenes are. Then from there we continue to nomenclature and the rest. So, allow me to introduce alkenes. So, alkenes are just the second type of hydrocarbons that have got a double bond. They have at least a double bond, at least one double bond, the carbon-carbon double bond in their molecules. So have at least one double bond, between the carbon-carbon atoms in the chain. The first thing that you need to know. Secondly, we look at their structures. This is how the double bond. How do we show the double bond between the carbon-carbon bond? It is shown in this manner. So the carbon-carbon double bond is shown in this case that each carbon atom has got other extra two that are shown, not straight as you can see. So this is the functional group. The functional group. Now, much as I've said that all members of alkenes must have at least a double bond in between the carbon-carbon bonds, it means that the minimum double bonds that any alkene member can have is one, but can have more than one, can have two or more. But for this case, we shall look at, in most cases, those that we shall deal with are those that have got only one bond, and also a few of them have got two. So the third thing that you need to know about alkenes is that the ratio of the carbon-hydrogen, carbon-hydrogen is low. Low ratio of carbon-hydrogen. So this is about the introduction part of the alkenes. So next we shall do the nomenclature in alkenes, and we find that nomenclature in alkenes is just the very same as in alkenes, only that we find that the names in this case end with the suffix ene. So you have the nomenclature. So all members of alkenes end with the suffix ene. That's what you need to know. So I'll have a summary of the first members of alkenes. In this case, the first member has got the minimum number of carbon atoms, which are two, not one. Only alkene members have got the lowest member, the carbon atom of just one. So in this case, I'll have a table to summarize on this. In the table, shall have two columns. The first is for the name. The second column, we have ethane. The first member is ethene. Second member, propene. Third member, butene. Fourth member, pentene in this case. So I'll write the formulae of these compounds. So in this case, we have the molecular formula. So for ethene, we have, at least to show the bonding, shall have the open structural formula so as to show the bonding. Open structural formula. Structural formula. So here we have CH2, CH2. For propene, CH3 this way. CH2 this way. For butene, CH3, CH2, CH, then CH2. For pentene, we have CH3, CH2, CH, CH2, CH, a double bond, and a CH2. So this is all about the summary of the nomenclature, so that we can see how all the members end with the suffix ene in this main. So moving forward, I want us to move to isomerism in alkenes. Isomerism in alkenes. Now, isomerism in alkenes are of two types. The first one, we have branched isomerism. Branched isomerism. Now, in branched isomerism, like in the member, like in the first one, I want us to look at, we take pentene as an example. Pentene then the formula of it is CH3, CH2, CH, double bond, and the CH2 this way. This is the molecular formula of pentene. So about the branched one, as we said before, during alkenes, we find that the alkyl group, the methyl group, like in this case, that forms the first molecule of pentene, need to be detached from it. Then we attach it to any middle carbon atoms. So should we detach this methyl group, that is the CH3, we find that how many molecules will be left in this chain? It will be 1 CH2, 1, 2, 3, 4. So therefore, among the 4 left, only two will be middle, a CH2 and a CH. So in this case, the first isomer we get of pentane is when we attach this methyl group, either of this, that we'll be having. We remain with the CH2 here, CH2, CH double bond CH2. When we touch it here, so that we have a CH3 here. One of the atoms here will be attached to this one, so that we have the last molecule as a CH3. The last molecule must be, remember, each carbon atom must be bonded by 4 bonds. So therefore, you shall have 3. That we have CH3, CH, then this will be a branch here. Hence, a branched isomer. So whose name will change? The name will change. The name will change. How do we name this? The naming or giving names in alkenes is the very same as is done in alkanes, and also will be the very same as we shall be doing in alkynes. So in this case, giving the position on which the methyl group has been attached is attached on carbon number 2. Now, using the rules, we find that in alkenes, since there is a double bond, we normally show the carbon atom to which that double bond exists. So in this case, we give the group first. So we must begin counting the number of carbon atoms from the side nearer the double bond, not where the branch is. That is a bit different from giving names in alkenes. So that in this case, we shall be numbering from this side, because we have 1, 2, 3, 4. So that we find that the branch is attached on carbon number 3. So therefore, we shall be having 3-methyl. Then the parent name will depend on the number of carbon atoms that are on the chain that are left after detaching the methyl group to be used as a branch. So therefore, since there are 4, so the parent name will be but. And as I said that in nomenclature in alkanes, that the suffix end with ene. The suffix is ene, so therefore shall be adding there. Before you add the suffix, you must include the carbon atom on which that double bond exists. If it exists in the first carbon atom, then therefore you are free to write, to just include the suffix ene, or you can use that carbon number 1 as using hyphen between the parent name must be but hyphen 1 to represent the carbon number in which that double bond exists, before you include finally the suffix ene. Therefore, the name becomes 3-methyl but 1-ene. Remember, the name can be 3-methyl but 1-ene, or can be 3-methyl butene, because should the double bond exist in the first carbon number, then, as I said, you can choose to use the position, which is position 1, or forget about it. So it therefore means that pentene can be read as pent1-ene, this one, pent or pent hyphen. When used, including the positions to which the double bonds exist, you must use 2 hyphens. The first being between the parent name and the position. So we have hyphen there, pent hyphen 1, another hyphen, then include the suffix ene. This way, that the name can either be pentene or pent1-ene. Now, so another possible way is when we attach this methyl group on this carbon number 2, so that we'll be having CH3, CH2, C, double bond there. Then we have CH2. So how will the name be? Different. It will be now 2-methyl, because it is in the methyl group is attached on carbon number 2. So we have 2-methyl but 1-ene. That's another name. So it therefore implies that there is no any other branched isomer that can be formed other than these three. So the first is itself, that is pent1-ene, that's the first isomer of butene or but1-ene. The second is 3-methyl but1-ene, and number 3 we have 2-methyl but1-ene. But in exam cases, you'll be asked to write the possible isomers that a given compound can form. So that is normally very open. So it doesn't matter whether you are writing a branched isomer or a positional isomer. So let's move to number 2, that is positional isomerism, so that we can see how many positional isomers that pentene can form, that we can have the total number of isomers that pentene can form, that is branched and the positional ones. So number 2 we have positional isomerism. Positional isomerism. Positional isomerism. So the word isomerism comes from the word position. And how do we form isomers in this? We do so by simply moving the double bonds in positions. From the initial positions, we move them. So we shall find that when you move the position of the double bond, then there's a likelihood that the name a new substance or a new compound will be formed with a different name from the initial one. So having pentene molecularly written this way as CH3, CH2, CH2, CH, a double bond and a CH2 molecule. In this case, we find that the double bond exists in carbon number 1, because you know when numbering you can count from any side. So you know that it is attached on carbon number 1. We find that should we move this position of the double bond to between carbon number 2 and carbon number 3, a new substance will be formed. That will be, will be but2-ene. You know, but2-ene and the but1-ene are different. So they are different isomers. So that we shall be having this. Move this here to here. We'll be having CH3, CH2, CH2, a double bond there, then CH2, CH2. So that it is named as pent -2 to show the position where it has been moved to. We have pent2-ene. Now, when you look at any other way, should we continue moving the double bond? So that should we continue moving it to the third, between the third and the fourth carbon atoms, shall find that the name will be very same, because now we will be compelled to begin numbering the carbon atoms as per number 2 from the left hand side. So the name will be the same as that which we've gotten, that is pent2-ene, because the double bond will be on carbon number 2. Carbon number 2. So should we move it between carbon number 1 and carbon number 2, it will be on carbon number 1. So therefore the name will be still same as pent1-ene. So therefore it implies that there is only one possible positional isomer that pentene can form. So in total, there are 4 total isomers that pentene can form. The 3 branched ones, as you can see here, and of course the one existing positional isomers. And that is all about isomerism. All the rest, the technique on how we've gone about this, and how both the branched and the positional isomers isomerism applies in all others. So allow me to continue the next or above this. So next we shall discuss preparation of alkenes, chemical preparations of alkenes. Preparations of alkenes. Now, there are only two ways. You find that there are two ways in which members of alkenes can be prepared. The first way is by hydration. The first way is by dehydration. So dehydration, as you know, just a chemical reaction that which contributes to the withdrawal or the removal of the water molecules. So in this case, the most common dehydrant in chemical reactions is normally concentrated sulfuric 6 acid. So we shall be using that in this process. We have this dehydration reaction. So when we react a member, I'll be using the first member of alkene as a case study, as an example. That is, so ethene, written this way, CH2. So ethene, I want to react this ethene and hydrochloric acid in a chemical equation manner. So ethene, CH2 is a gaseous substance plus sulfuric 6 acid, in this case, is a compound. Then the state symbol will always be liquid, not aqueous. So in liquid state. So when you react this, this we need to dehydrate ethanol, not ethene, ethanol, because you cannot dehydrate a gaseous substance. You shall dehydrate ethanol. When you bubble molecules of ethene into water, you form ethanol. So ethene molecules bubble in water, you form ethanol. Ethanol, written as C2H5 and the OH, because it is one of those compounds that contain the OH functional group. So this is ethanol reacting with sulfuric 6 acid. So in this case, should you add some molecules of ethanol and to conc sulfuric 6, hydrochloric 6 acid, it will be dehydrated to form an unstable compound called ethyl hydrogen sulfate. Ethyl hydrogen sulfate. Ethyl hydrogen sulfate. So ethyl hydrogen sulfate is chemically written this way as C2H5 OS2OH in this case. This is the chemical formula of ethyl hydrogen sulfate. Now, this formed a ethyl sulfate when heated. When heated, it forms ethene and water. When you continue heating this one, it forms so CH2, C2, H5, or S2, or H. This is in liquid state. It will form ethene, that is C2, H4, or C2, or CH2, same as C2, H4. This is ethene gas, of course, plus water. So this is how water will be, a member of alkene. In this case, the first member, this ethene gas, will be prepared by degradation process. So the second way, or the second method, is by cracking of alkenes. Cracking of alkenes. Number 2, cracking of alkenes. Now, in cracking of alkenes, there are other two ways in which this can be done. So there are two types of cracking of two methods. So the second way in which you can chemically prepare members of alkenes is by cracking of alkenes. In cracking of alkenes, there are two methods. Number one is the first type of cracking of alkenes is called thermal cracking. Thermal cracking. Thermal cracking. Now, the word thermal is a chemical term that refers to heat energy. So in this case, we need to just subject or supply a high amount of heat energy to the long chain members of alkenes, because you know that they're normally useful in the short chains. Short chains alkenes are those that are usable. So that's why there's a need for them to be cracked or be broken down. Cracking just means the breakdown, that which is done to the molecules of the long chain alkenes into smaller ones. So in this case, we need to subject them to a high amount of heat energy, and that's the only condition that is required here. So the amount of high amount of heat energy, that is high temperatures between 400 to 750 degrees Celsius or centigrade. So in this case, this is a very high amount of heat energy. So should we subject these long chain alkane members to this, the energy, the temperature in between 400 to 750 degrees Celsius will be broken. They'll be broken into the smaller alkenes, and of course hydrogen. And that's why we find that one of the uses of alkenes is that as they are sources of hydrogen. So I'll wrap up here so that I can explain in a chemical equation cracking of alkenes. So, for instance, if you have maybe propane, or let's take a case of propane of ethane, CH3. This is ethane gas. Now, when you subject it to high amount of energy, that is, write that on the R because it is a condition, it is a catalyst. to 750 degrees Celsius. So we found that a lower member will be formed. Like in this case, should you heat it, methane, you'll be forming methane as a lower member of alkane, that is methane gas. You will form the next two members of now alkenes. So therefore, you'll have methane, shall have ethene plus propene, CH3, CH2, double bond, CH2 plus hydrogen. So we can summarize this by saying that should we break an alkane member, for instance, ethane, we get methane, this methane, we get ethene, we get propene, and of course hydrogen gas. So this can be summarized by saying that should we break any member, should we heat any member, subject any member to extremely high temperatures between 400 to 750 degrees Celsius, the long chains in them will be broken into smaller alkane members, alkenes, and of course hydrogen. That's what you need to know. Now, number two, another way in which cracking of alkenes can be done is by what we call catalytic cracking. So, number two, catalytic cracking. Catalytic cracking comes from the word catalyst. So in this case, it therefore implies that in this cracking method, a catalyst will be used. And of course, not only a catalyst, and also some amount of heat energy. Yeah. And not only a high amount of heat energy, but also some pressure also need to be included here. So in this case, there are three conditions that if should you be asked to state the conditions that are necessary during catalytic cracking of alkanes, there are three. You must be specific. Which range of temperature? What amount of pressures, and in which unit? Is it in atmospheric pressure? Is it in whichever unit of pressure? You need to know. So in this case, and of course, lastly, the specific catalyst that is used. So here we find that the range of temperature here, temperature range, is a relatively low. So we have a range of subject the long chain members of alkanes to a lower amount of temperature than just the thermal. So in this case, around between 400 to 450. So it should be a maximum of between 400 to 450 degrees Celsius. So, and there must be a pressure of around 135 atmospheres. This pressure is a very high amount of pressure. And of course, there is a catalyst. Which catalyst? The catalyst that is a mixture of these two. There must be a catalyst. Which is a mixture of silica. Silica is just an oxide of silicon. So this one here, silicon 4 oxide. And of course, alumina. Alumina is just an oxide of aluminium, chemically written this way. So in bracket, the chemical formula of aluminium is this: Al2O3. This is the alumina. So a mixture of this is normally what is used as a catalyst. Now, why do we have to include a catalyst in this type of in this method of cracking of alkanes? so as to ensure that the breakage of the long chain alkanes is achieved at a relatively lower temperature. You can find that the temperature here is relatively low than in the thermal cracking that needs only extremely high temperatures as the only condition. So this is all about that. So allow me to wrap this off. Now, moving forward, I want us to learn the chemical properties now of alkenes. Chemical properties of alkenes. And in the chemical properties, we shall begin with the number one, that is combustion. Combustion is just but burning process. So in this case, like any other hydrocarbon, alkene members, when burnt, when burnt in complete supply or in sufficient supply of oxygen, they form carbon dioxide and water. So having an example, like in this case, shall have ethene, CH2. When you heat this, it will react with atoms of oxygen because it will be oxidized to form CO2, that is carbon dioxide, of course, plus water in this manner. Let's balance our equation, because the equations balance differently when there is sufficient supply of oxygen and when there is insufficient supply. So this is when there is excess or sufficient supply of oxygen. Excess oxygen. So it forms this. So you can balance this. So carbon, there are two atoms here. This side is one, so you can put here tentatively to balance carbon on this product side. But carbon balanced. Hydrogen, 2 plus 2, those are 4. On the right hand side, product side here is we have 2 atoms of hydrogen. So should also put another 2 here that we can balance hydrogen. That we have 4 this side, 2 by 2, 4, 2 plus 2 here, we have 4. So last we have oxygen. Oxygen here, there are 2 atoms on the right hand side. Product side, these 2 affects even this. So therefore, here 2 molecules by 2 atoms of oxygen get 4 in total. Here we have 2, so that we have 6 oxygen in the product side. When we have only 2 in the right hand side, so therefore, by either division or multiplication, how do you make these 2 atoms of oxygen be equal to 6? Multiply by 3, 2 by 3. So we put 3 here in the molecular side, so that the equation of the combustion of ethene in excess supply of oxygen balances in this case. It requires to completely react with 3 molecules of oxygen to form 2 molecules of carbon dioxide and another 2 molecules of water in that manner. Now, should there be insufficient supply of oxygen, what are formed are just that the unstable oxide of carbon, that is carbon 2, that is CO. So we have CH2, that's the molecular formula of ethene, CH2, another CH2, reacting with oxygen. The molecules are not affected, whether there is excess or insufficient supply. So this is insufficient oxygen or limited oxygen. So it will form CO plus water. what is a common compound formed. So in this case, we will balance this, you know that they balance indifferently. So in this case, carbon 2 atoms, here 1, so that you can put 2 here. Hydrogen 4 here, this side you can put 2 here. Oxygen here now 4 here, so you can put 2 here. So we find that in insufficient or limited supply of oxygen, members of alkenes, in fact all members of hydrocarbon, not just alkenes, do react, are oxidized with low amount or low molecules, or fewer molecules of oxygen. Like in this case, this ethene can only react with the 2 molecules of oxygen to form the unstable carbon dioxide and of course water in this manner. So as you can see, so this is all about combustion of the first chemical property of alkenes. Number 2, we move to addition reaction. Number 2, addition reaction. In addition reaction, there are quite a number of subtypes of addition reaction that one needs to know. The first one is hydrogenation. Now, in hydrogenation reaction, this involves the reaction, the oxidation of the members, the oxidation of the reaction of hydrocarbons, the alkene members, with more molecules of hydrogen to form what? To form, alkene members. So in this case, for instance, using the case study as ethene. So ethene, CH2, reacting with a molecule, 1 molecule of hydrogen this way. Because as you know that hydrogen is the atomic substance or gas. So in this case, the double bond, when I write the open structural formula of this, it means that I can show the bonding, it exists this way. We'll find that should we add react these gaseous, the gaseous ethene and hydrogen, the hydrogen will break. The bond between the hydrogen will break, so that the double bond, the carbon-carbon bond, double bond, will also be broken, so that to give the free electrons, so that which will accommodate the broken atoms of hydrogen from a molecule of hydrogen in this case, so that we can form ethane this way. So even other members of alkanes can be formed should we react them with molecules of hydrogen. That reaction is what we call hydrogenation type of addition reaction. Now, this is Roman 1, hydrogenation reaction. Roman 2, type of addition reaction. We have halogenation. Halogenation. Halogenation reaction comes from the word halogen, and halogen is a chemical name of the members of group 7, including fluorine, chlorine, bromine, and iodine. So in this case, should we react the members of ethene with the molecules, with the atoms of members of group 7, that is halogens, then that is this type called halogenation. So for instance, we have ethene, CH2 reacting with the let's say reacting with the chlorine. So, and chlorine also, all members of group 7 are also are diatomic, form diatomic substances because they are made up of 2 atoms in each molecule. So in this case, the double bond in the ethene will be broken so as to give the free electrons that which will accommodate the 2 atoms of chlorine in this case. So that it will form, the double bond will be broken in this case, so that we have CH3. Yeah, so you find that when ethene reacts with the chlorine, it forms 1, 2, should be 1, 2 dichloroethane. 1, 2 dichloroethane. Why? Because when the double bond is broken here, that will be having something like this. The existing hydrogen atoms, the 2 atoms of hydrogen in each atom will be left as like that is that, leaving a valence of free electrons that accommodate the colored atoms this way. So that this is the open structural formula of the 1, 2 dichloroethane that is written molecularly in this case as CH2, CH2, Cl2. So that's what happens. So that is just an example of halogenation. So the same happens with other 3 members of halogens, including fluorine, so that it can form 1, 2 difluoroethane. It also happens with the bromine to form 1, 2 dibromoethane, and also iodine to form 1, 2 diiodoethane. So moving forward, the third type of additional reaction other than halogenation and halogenation, we have allow me to rub off here as we continue. The third one, we have Roman 3. We have addition of halogen bromide. Hydrogen halide. Hydrogen halides. Or reaction, because we are using the word addition, so to avoid repetition, let's use reaction with hydrogen halides. Now, halogen halides are different from, it normally confuse learners from halogenation. Halogens are just the members of group 7, but halogen halides are new compounds that are formed when hydrogen atoms of hydrogen react with members of halogens. That's what you need to know. For instance, I'll take the first case that, of course, you are using a case study of ethene, that is CH2, reacting with an example of hydrogen halide. Maybe you have hydrogen chloride, because chloride is an atom of chlorine, it's a member of halogen, reacting with an atom of chlorine to form an example of a hydrogen halide, that is hydrogen chloride, HCl. G, because it is in gas state, it's never in liquid state. So is the first member when chlorine forms hydrogen halide. Now, bromine, we have hydrogen bromide. We have other numbers like hydrogen bromide, like HBr. We also have hydrogen iodide, HI. We also have hydrogen fluoride. So these are the hydrogen halides that you need to know. So let's see what happens when we react, this ethene and this hydrogen chloride. Now, what will happen is that the double bond will break in a member of alkene, that is here, double bond here, hydrogen, hydrogen, hydrogen. So the double bond, when double bond breaks, so to give the leeway for the attachment, for the accommodation of the incoming, foreign atoms. So the hydrogen atom, the hydrogen chloride will also be broken. The bond, the covalent bond that hold the atoms of hydrogen and chlorine in the hydrogen chloride will be broken, so that we have the single bond remaining. They had two hydrogen atoms remain in each carbon atom, as you can see here. So in the first molecule, you can attach any. You can choose to attach a hydrogen. If you do so, then you have to attach a chloride atom in the second molecule. So or vice versa, chloride and then hydrogen, that it forms this structure. Means that it forms CH3 in the molecular state, CH3, CH2, Cl, and you can name it. You can name it as chloroethane. It's named as chloroethane. Chloroethane is a gaseous substance, so it only forms chloroethane. There is no any other product formed alongside it. So therefore, that when ethene reacts with iron chloride, it forms what? Chloroethane. When it reacts with hydrogen bromide, it will be forming bromoethane. If at all it reacts with hydrogen iodide, it will be forming iodoethane. And finally, it reacts with hydrogen fluoride, it will form fluoroethane. So therefore, it implies that in this reaction. Okay, so the fourth type of addition reaction, that is polymerization, or we can call it self-addition. Why is it called at times self-addition? This involves, the union of the molecules of members of alkenes. In this case, since we were using ethene, so for example, we have ethene in this manner. So we have the units of members of alkenes that in this case tend to unite. Before they unite, we have the union of members of units of alkene members. So in this case, how do we call the units of alkene members that unite during this type of additional reaction? They are called monomers. Monomers. So each unit or each monomer need to unite or combine with another, so in a continuous reaction, so to form a long chain of a compound that is called polymers. So addition reaction involving monomers. So one monomer, a monomer plus another plus a monomer forms polymer. So polymer is just a unifying name of the compound that are formed when the repeated units of monomers come together. So, but they have got their individual names. So, for example, ethene forms a monomer. So when ethene combines with another, it forms polyethene in this case. So how does that happen? The molecule, the double bond between the carbon-carbon atoms in ethene, like in this case, have to be broken. So when they break, they tend to create, the free electrons which will accommodate or will accept the bond that which will be connected to the next carbon atom in the continuous chain. So in this case, we will be having C. This is monomer combining with another, in this case, hydrogen, 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 hydrogen. So the polymer will be formed in this case. One of the double bonds will break, leaving only one. So in this monomer we'll be having only a single bond between the carbon-carbon atom. Of course, you can see in each carbon atom there are two hydrogen atoms that must remain as they are. That we have hydrogen there, hydrogen. So they must be straight because in this case they must be straight because there is a free electron that is created, that which will accommodate, the double bond, the bond in the continuous chain. In this case, that we have another bond, single bond, connecting to the first carbon atom in the other monomer, then another single bond that was left after the two broke, so that it is continuous. So they are continuous. So in this case, he has two hydrogen atoms, as you can see. They formed polymer, like in this case, it is a continuous process of the union of the monomers, several monomers, so that leads to infinity. So to show continuation, it is always imperative that you introduce a bracket, and the bracket must cut that continuing bond. So it must cut to show continuation. Then write an N as a subscript on the lower right hand side of the polymer there, to show that this N here shows the number of repeated units that combine to form the polymer. So in this case, you can always name the specific monomer, polymer. In this case, it is ethene, because the monomers that are combining are those of ethene. So the name of a polymer therefore becomes poly. Poly becomes dominant prefix. So, and the suffix will be coined from the monomer, that which combine with the other. So we have polyethene. Now that's all about that. So moving forward, we'll learn the rest of this, so that we move to the next two. So number 3, we have acidified. We have reaction with acidified potassium manganate 7. Manganate 7 in this case. So the chemical formula of it is this. Potassium manganate 7, written this way. Now the chemical formula of acidified potassium manganate 7. Acidified because because some it has a solution of it has been prepared. So a solution of a prepared crystals of potassium manganate 7 is called acidified. So that in this case, it acts as an oxidizing agent. Should we use our ethene member here, like C double bond, hydrogen. In this case, should we add some molecules of the acidified potassium manganate 7 onto the molecules of any member, like in this case ethene? You'll find that ethene member here will be oxidized. When the double bond will be broken, so that when the double bond is broken, it will form something like this. You know, the potassium manganate 7 here. So the manganate 7 ion will be donating oxygen atoms dissolved in a solution. So therefore, the manganate 7, this one, or will be adding hydrogen, oxygen, so to form this compound. So it will be in the form of solution. There will be formation of the OH group, functional group, that will be attached in each carbon atom in this ethene member. That we have OH here, another OH here. So of course, there are two atoms of adenine that will be attached, as you can see. So this is the number that will be formed in this case. So we have CH, OH, another carbon atom attached in that. So this is a new compound that belongs to a group of compounds that is called diols. So diols. So a group of compounds that are called diols are those compounds that contain two of the OH hydroxide functional group. This one. So it therefore implies that should we add the acidified potassium manganate 7 onto the members of ethene, there will be oxidation. So there will be donation of the hydroxide group, the two molecules of them that will be attached into the alkene. So you find that since this reagent has been acidified, so therefore remember, any other acidic substance is able to emit hydrogen ions, that which will react with oxygen ions to form the hydroxide group, that which will be added onto this. So what will happen is that the purple manganate 7, solution will be changed, will be decolorized. So it will be changed from purple to, because the manganate 7 ions will be reduced to manganese 2 ion, which are colorless. That's why the color of the formed solution, product here, won't be purple as that reagent. Of course, the members of this are normally colorless. So they will be focusing on the colored reagent, that is manganese 7, acidified potassium manganate 7, which is purple due to the presence of the potassium manganate 7, which will be reduced to manganese 2 ion, that which are normal colors, and that's why the resultant compound formed is colorless. So the name of this our diol compound is 1,2-ethane diol. 1,2-ethane diol. That's the name of this, as when you name it. Now, allow me to wrap up this, that we number 4, very fast, we have reaction with acidified potassium chromate 6 ion. Chromate 6, the chemical formula of that is K2, this one, so this is the chemical formula of the acidified potassium chromate 6. So in this case, this is normally orange in color. It is orange in color, that's what you need to know. An orange reagent. It is orange because of the existence of the potassium chromate 6, because of the chromate 6 ions in it. Chromate 6 ions are normally orange in color. So whenever we add it to a member of alkene, for instance ethene, you will find that the orange color will turn or will change to green because of the reduction of the chromate 6 ions, which are orange, to chromium 3, So the chromate 6 ions are reduced to chromium 3 ions. So these ones I said orange, chromium 3 are green in color. So in the end result, we find that the formed product will be generally green, not orange. So that is all about that. So the last two, another one, we have a reaction. Reaction with concentrated sulfuric 6 acid. In this, we find that we take a member, for instance, ethene, like CH3, C double bond. In this case, we react it with conc sulfuric 6 acid. In this case, liquid state, what will happen is that it will form one compound called ethyl hydrogen sulfate. Ethyl hydrogen sulfate, in this case, ethyl hydrogen sulfate, that is C2H5OS2OH. This is ethyl hydrogen sulfate. Now, there are two reactions that will take place. There will be two reactions taking place. The first one is this: you have the alkene member with the conc sulfuric acid to form ethyl hydrogen sulfate, written this way chemically, which is in liquid state. Now, so the next process that you take the formed ethyl hydrogen sulfate, then you add water into it. You add water into it. Then you gently warm. When you add water into this, so C2H5OS2OH, you add some water molecules into it, then you warm. When you warm, these two compounds will react to form two substances, to form ethene C2H4, of course, plus dilute the chloric acid, sulfuric acid. So then this gas will be collected. Now that's what happens. Finally, allow me to wrap off this as do the final one, number 6, chemical property of alkenes.
I'm working on a 2 minutes. Honestly.
Okay, the 6th one and the last one is the reaction with bromine water. Bromine water. Now, bromine is just a halogen molecule, halogen is in group 7, amino group 7, whose molecules, when bubbled through water, forms a solution called bromine water. Now, that bromine water has an acidic substance, contains an acidic substance called hypobromous. Hypobromous acid. Just like when you bubble chlorine in water, it forms chlorine water, which contains two compounds, that is hypochlorous acid or chloric 1, and of course, and hydrochloric acid. So in this case, this hypobromous acid is responsible for the action or for the change of the color should we add the molecules of bromine water and to the members of these alkenes. For instance, when you add it to any member there, what happens? Remember, bromine molecules are normally, the molecules of bromine gas are normally brown. Bromine gas. But when you bubble the molecules of bromine vapor or gas in water, it forms a yellow solution. So bromine water is therefore yellow. So when you add the yellow bromine water into any member of alkene, so the yellow color will be decolorized. After the process or the reaction, so the yellow bromine water is normally decolorized should we add it into any member. Okay, so lastly, the uses of these alkene members. Number one, alkenes members are used to manufacture plastics. Number two, they are used to manufacture ethanol. As you've seen, they are used to manufacture detergents. And number three, they are used to prepare 1,2-diol, which is used as a propellant in machine and also used to prevent knocking of the machine engines. And lastly, we have ethene. Ethene specifically is used in ripening of fruits. Ethene used in ripening of fruits. And finally, that's all about this alkene members. So I want to thank all the viewers for their time for viewing this video. I want to welcome you once again to Proficient You Education Services. This is where we value, we inspire. We inspire education services. So welcome so much.